All right, let's have a look at question 3. This question is about a tennis ball thrown vertically upwards and then bounces once and hits the ground again. So this is a vertical projectile motion question. So you're thinking importantly about declaring sign convention, being careful of what's positive and negative, and using your equations of motion. Let's have a look. Firstly, the mass is given as 57 grams. Just flag that, because if we use it, our SI unit for mass is kilograms, and so we'd need to change there. It releases the ball 1.85 meters above the ground, so that distance between the hand and the ground is 1.85 meters. Notice that's distance. If we're going to use the vector quantity of displacement, then we're going to need to be really careful about whether it's positive or negative. We'll get back to that. It takes 1.3 seconds from the moment it's released till it strikes the ground. So that path in yellow, highlighted in yellow, takes 1.3 seconds. And it rebounds back up to a maximum height of 1.4 meters. Alright, so that's the setup. Let's now look at each question. First question asks for the initial speed of the tennis ball as it's thrown upwards. Now notice the use of the word speed, so we're looking for a vector quantity, a scalar quantity. We're not interested in direction, but obviously the direction's upwards of the initial velocity. So the initial velocity VI is what we're looking for. First thing to do is to declare sign convention. We'll take up as positive, and let's just state that. It's quite a good thing to do in your exam, is to state specifically in words the direction that you're going to take to be positive. Alright, let's get our shopping list out. VI is what we're looking for. The time for that journey, highlighted in yellow, is 1.3 seconds. That was given in the question. Acceleration is acceleration due to gravity, so it's 9.8 meters per second squared, and it's minus because we've taken positive to be up, so minus 9.8. Now delta y, we need to be really careful with this. Delta y is the displacement between where the ball starts and where it finishes. So if we draw a vector in our diagram, then we start at the hand and the ball finishes on the ground. And so delta y is from where it starts down to where it finishes. So notice the direction is down, and according to our sign convention, that's minus. So delta y is minus 1.85. Now this is really important. Many people make a mistake there and indicate plus 1.85 and then get the answer wrong. Alright, let's pull out the formula. Delta y is VI delta t plus a half AT squared. That's in your data book, so don't get it wrong. Make sure you copy it down correctly. And then we substitute. Our delta y is minus 1.85. Once again, just to highlight that, it's really important that you get the negative sign in there because the displacement is downwards. VI is what we're looking for. Delta t is 1.3. A is minus 9.8, and our t there is 1.3 squared. And if we solve for VI, it's 4.95 meters per second. And remember that the question asks for speed, so we don't have to indicate a direction. Alright, 3.2. Calculate the speed. Again, notice the use of speed, so we're looking for the scalar at which the tennis ball leaves the ground after it's bounced. Okay, so we're looking for speed. We don't have to indicate direction. And so we're looking for that initial velocity after it's just bounced. Okay, so VI is what we're looking for. Alright, if we consider the period from when it bounces up to when it reaches its highest point after the bounce, then that final velocity is 0. And so our VF is 0. Acceleration again, minus 9.8. And delta y, in this case now, is from the ground up to where the ball is, and so that's a positive displacement because it's in the up direction, and we've taken a sign convention that says up is positive, and so that's a positive 1.4 meters. Alright, our formula is VF squared, because VI squared plus 2a delta y. Final velocity up at the top of the bounce is 0. Initial is what we're looking for. A is minus 9.8, delta y is 1.4, and so our initial velocity is 5.24 meters per second up, but they just want the speed, so that'll do. There is another way to solve this problem. You can use a conservation of mechanical energy, and in this case the EP up at the top is equal to the EK at the bottom, and if you substitute in there mgh equals a half mv squared, you can also use that formula to solve for the velocity. Alright, 3.3. assuming the ball strikes the ground at a speed of 7.79 meters per second, show using suitable calculations that the collision is inelastic. So we're interested in the ball coming down, and its final velocity we are given in the question of 7.79 meters per second down. It then collides with the ground and then heads off up at some other velocity which we've just calculated. And so it's that collision that we're interested in showing is inelastic. So to do that, we have to calculate kinetic energy before. It's a half mv squared. Remember, the mass is 57 grams, so we have to divide it by 1,000 to get to kilograms, so 57 over 1,000. And our velocity just before impact is given as 7.79, so we square that. Remember that energy is a scalar, so we're not interested in direction. So the fact that it's minus 7.79 we will ignore. Of course, once you square it, that would disappear anyway. So that gives us a value of 1.73 joules for the kinetic energy of the ball before the collision. If we look at kinetic energy after, again, half mv squared. The mass I've just put in there is 0.057, that's 57 over 1,000. And we calculated in the previous question that the velocity after the impact is 5.24. And we square that and we get 0.78 joules. And so we can conclude from that the EK before is greater than the EK after, so some energy is lost during collision, and therefore the collision is inelastic. Remember to finish off your answers nice and neatly to indicate exactly what the question's asking. All right, 3.4, the magnitude of impulse of the ball when it bounces. Again, impulse calculations most often deal with objects changing direction, and so our sign convention is crucial. Now, we have declared it for this question, but sometimes it's helpful just to remind yourself. We're going to take up as positive. So impulse is given by F delta t, and that equals the change in momentum, or m delta v. And if we just write out change in velocity is final velocity minus initial velocity. So the mass of the ball is 0.057 kilograms. Final velocity is 5.24. Make sure you notice that that's an upward velocity, and therefore it's plus 5.24. And then we need to subtract the initial velocity, which is 7.79 down, so it's minus 7.79. So just be careful of those signs that you don't get mixed up. And that gives us an impulse of 0.74, and note the units kilograms meters per second. 3.5, the ball in contact with the ground for 0.02 seconds. Calculate the force the ground exerts. So F delta t is our impulse, and we've just worked out our impulse at 0.74. And so F times delta t is 0.02 equals 0.74. We solve for F, 37.14 newtons. Now force is a vector, so we need to give a direction. It's a positive value, and therefore it indicates an upwards force, and obviously the ground exerts an upward force on the ball as it bounces. Alright, 3.6, velocity time graph for the motion of the ball from when it's initially released until it hits the ground for the second time. So this is quite a long question. Let's go through it step by step. Start by drawing our axes. We draw positive and negative velocity axes because we have motion up and down, and our time axis. Notice I put the units in. If you know the units, then you're expected to put them in. Alright, let's go step by step. Our initial velocity upwards, we calculated right at the beginning as 4.95, so we can indicate that at t equals 0, our initial velocity is 4.95, that's a positive value. Then up at the top, the highest point, the velocity is 0, so that's another point. At a certain time, the velocity is 0. And then at the bottom of that first part of the motion, the final velocity there, we calculated it, it was given in the question as 7.79, and that's a negative velocity because it's downwards. And so there we have our first 3 points, and we know that final velocity, it took 1.3 seconds, so we know that point of minus 7.79 is at 1.3 seconds. All right, now because it's falling under gravity, the acceleration is constant, and so a velocity time graph will have a constant gradient because the gradient gives us the acceleration, and so we can confidently draw a straight line through those 3 points. Alright, it then stays in contact with the ground for 0.02 seconds, and so we know that at 1.32 seconds it's now going to start its journey upwards, and so that's the initial velocity after the bounce, and that was calculated to be 5.24 meters per second. Up at the top of that bounce, the velocity is 0, so once again we're across the time axis, and then it carries on down and we'll have some final velocity which we don't know, and so we don't give it a value, but we do know that it'll form a straight line, and so we'll have a straight line through those 3 points. Now what to do between the 1.30 and the 1.32 seconds? Some people use a dotted line. I think it makes sense just to join those 2 points through the 1.03 seconds, and that then gives you your complete graph.